It's August 21st, and it's a report for Artizen Fund about LunCoSim progress. LunCoSim, it's a multi-physics simulator for space missions. Technically speaking, it's a collaborative, interactive, multi-physics robotic co-simulator for space missions. I know it sounds a bit hard, but essentially it means that our simulator is designed to simulate all the aspects of spacecraft subsystems like thermal subsystem, hydraulic subsystem, electrical, and so on. During season 6, we've made a huge progress. Finally, now we have a pretty decent basic simulator. As an example, we are working on implementing one rover mission. So now you can see the interface of our simulator. Here you can see the real terrain from Apollo 15 mission, and we have designed a simple rover. That's the visualization of the rover that can traverse that terrain. The biggest thing is that this rover, it's just a visualization of a real rover. And what's the most important is that we are simulating right now only electrical subsystem. In the left part of the screen, you can see our telemetry structure. So we have like a battery. Now it's fully charged, so you can see it here. We have solar panels that are properly simulated. So the rover can move, all the physics is correct. We have features needed for planning your lunar mission, particularly when you plan your rover mission. You have to be careful of the slopes, because obviously on a slope a rover can tilt. So we have a mission overlay, what is safe and what is not. We can like change the boundaries. So now essentially there are almost no safe place on the screen, but let me turn it off. It's not so convenient. So essentially we have a rover, and we have an autopilot that can drive that rover. The thing that we are simulating actually all the subsystem of the rover. So now you can see the graph of available solar power, which will start changing when the rover will move to the inclined surface, because on the inclined surface the angle of inclination is different, different amount of sun gets to the rover, so you will see the drop of that power. So let me add second graph that shows available rover power. You can see it on the right side. So when rover is moving, it's consuming some energy. And what's important, these simulations, they are physically accurate. They're so-called continuous simulations. Let me stop the rover. Now, when I stopped the rover, you can see that the left part amount of energy stored in battery started to grow because it's charging from the solar light. We also have several different clocks. Like particularly, we can speed up 10,000 time cell clock. Basically means that now it's night, so solar system started to. Rover is no longer charging, solar power is close to zero. Now the sun is getting to, will raise again, and you will see how power gets back. So let's see, yes, now we have some electricity with and pause. The thing is it's just one example of what's possible to simulate. And it's not built into the simulator. In reality, we have like several models, mathematical models. Like for example, this is the model of a battery, like how it charges, it's up to physical laws, and you can reuse it. We have same model for same mathematical model for solar panels, for motors, and it's physically accurate. To create a simulation, most of simulations created nowadays, they actually simulate one specific case. And in those simulations, often like the mathematics and like everything what's going on, it's heavily tied in the simulator. So you have like your description of like formulas and solution how computer solves them. It's heavily coupled. In our case, the description of the models, everything that you can see, it's not built into our sim. You can easily run it separately. So like you can easily describe separately the like electrical subsystem. You can describe like the rover itself. It's described like that. What you see on the screen right now, it's a so-called USDA format used by modern simulation engines, and actually describe everything how your system looks like. You describe the assembly, and this format is both useful for humans and for rovers. And like here you can see like how outputs, like for example here we connect environmental variable sun mounting point towards electrical subsystem in the so essentially now anyone can do those simulations. I have to say that I have experience building real rovers for the moon, and this simulator addresses all of the issues that I faced with. And those issues mainly was that you have tons of disconnected models, and if you want, like you have a separate thermal model, mechanical model, and so on. And often you would have to pass the data from one model into another. Sometimes we even use simple papers to create the basic models and do some calculations. But then we had to input that information into other stuff. And LunCoSim addresses everything. We have a distinct so-called symbolic math kernel. We use a special library for that. It's called Rumoka. And thanks to that library, we can describe all the mathematical models in real time. And we can properly simulate all the aspects that of the mission that we are interested in. We also have tutorials. We are working on proper lender simulations. So, for example, we have like it's an early alpha version. It's far from perfect, but we have like a lender. You can see here, you can see that a lender model is much more complex compared to the rover model. In the rover model, we had around like 150 variables that we've been tracking, and here we have almost 900 variables that could be used to track the simulation. So here is a lender, every leg is simulated, it has thrusters, it has like fuel tanks, it has like pump fuel system like hydraulics. Unfortunately, I'm making a recording, so it's a bit slow. But yeah, like all that information, all the model you can see here. So we started LunCo a while ago, and initially it was made on Go the Game Engine, but in March a lot of things finally happened. Initial idea was to use simple basic tools to create basic simulations, but with the Godot, it became pretty clear that unfortunately it was too simple and it was not designed to run actual long-term complex simulations. So we made a tough decision to recreate everything from scratch using as programming language Rust, which is super fast and a lot of space software already using Rust, and I mean that it'll be easier to integrate with it. Also, Rust is super safe in terms of certain features, which makes it like a perfect solution for designing robust professional grade space software. So most of the time, frankly, during season 6, we've been building the simulation, and we made like at some point in time almost half a million of lines. Obviously, we are heavily using AI, and our simulator is built for AI. In reality, everything that you've seen here, the sim models, everything was made by AI, and it was verified by us humans that it's actually correct. So now, after frankly many years, we have a decent version on our GitHub in this repository in the releases section. And it was a long journey. One of the reasons why we decided to recreate is that a project called Rumoka, it's a Rust Modelica compiler, I think that's how it's called, was created. It's a tool for so-called symbolic math, and thanks to that tool we can accurately simulate all the subsystems, as I've mentioned, like hydraulics, electrical, thermal, all of that in one model. Actually, we are generating a huge portion of the model in real time. We have like a basic model described in Modelica, and we assemble those models in the standard that is called USDA, which allows us to have decoupled simulation, description of what has to be simulated from actual simulations. And it took a while, actually. I became a contributor of the Rumoka project. You can see it here, my PFP. Now it's August 21st, so the report is made after the season 6. So while season 6 mostly was dedicated to developing the simulator, a month ago, actually end of July, we got into the newsletter by Modelica Association. Modelica Association, it's an association that basically creates Modelica language. It's huge, like lots of huge brands like Bosch, like pretty, like a lot of brands use it. They're part of the Modelica Association, and we got into their newsletter, which is super nice. Here you can see a screenshot from LunCoSim of a so-called PID, proportional integrated differential controller. That's like an algorithm that heavily used to adjust parameters for a lot of dynamic systems in the world around us. So we got into their newsletter, and on July 21st, we ran the first in real life event. It was a so-called summer space school. Around 20 students joined us. You can find more information on our LinkedIn account. Here are some images from the event, and it was pretty successful. We learned a lot. I have to say the version was super buggy, but students were able to use our simulation software to run their own, to use the simulator to plan the route of rovers on the moon up to energy limitations and up to the terrain itself. We learned a lot based on that feedback. We have significantly updated our code, and frankly, I have to say most of the code was done by me, and I have to say that it's the most complex software that I've ever built. It's around 500,000 of lines. It has tons of features needed to, when you run the simulation. So, for example, it can record videos. Obviously, it's designed for AI, so AI and humans use the same paths for that. For like they have same capabilities. Also, a paper about our simulator was accepted to a so-called IAC, International Astronomical Congress. It's the biggest and maybe most impactful event in the professional space industry. Every year it happens in different cities all over the world. This year it'll be in Turkey, and around like 7,000 people all over the world, space professionals are coming there. So our paper was accepted, which is pretty nice. We'll be there in October presenting our simulator for this audience. Our simulator is open source, so anyone can use it, and now anyone can design their own space missions. You know, often when newcomers start to design, to build stuff for space, they start to do what they can do, not what has to be done. Oops. And so they're like, okay, like I want to build a rover, so I want the rover to look like that. But the issue is that the conditions they of the mission, they heavily impact the mission itself. This is in Apollo region. Apollo region was close to equator, so here we have our solar panels on top of the rover. And a while ago, you've seen that when the rover started to move on the inclined surface, amount of energy produced by rover changed, and such things has to be taken into account. So with our simulator nowadays, you can design your own mission. You can start with like high level requirements, high level stuff, and then go deeper and deeper and deeper to more and more and more precise model. And the simulator itself is built for interoperability, so you can easily reuse models created in our simulator in other stuff, in other software. You can well, easily share it with your teammates. So we have a collaborative mode where users can actually run the missions together in the same world, which is also pretty unique compared to other simulators. Thanks to Modelica Association, who liked our project, we started to create content on LinkedIn about system modeling, and we have a really good feedback from users. I mean, now every week we have like 20, 30 high quality engineers who work for NASA, Artemis mission, like all over the world from the top places. They start to follow us, and it's completely organic growth, which is like amazing. We are not pushing them. It's not like when you're spending hours and hours on Twitter trying to get some attention. So now people just like our content, and they are following us. Now the simulator is okay. There is a lot of things to be done, but yeah, thanks to Artizen, we can do it, and soon, hopefully during the season 7, we will have several strong use cases. So one of our use cases is this the rover. We're also working on lander, but we also started to work on a project that heavily on several projects that heavily relies on the capabilities of the simulator, like pretty serious one. But I will share information about those projects later. So thanks everyone for support, and as always, your donations are much appreciated. Bye bye.